Section 21.3. Wave functions must reflect the indistinguishability of electrons. In short, electrons are indistinguishable. Imagine you are looking at a water molecule. It contains 10 electrons. Let's label these 10 electrons, and then randomly I swap electron 8 and electron 2. You will not be able to tell the difference. So again, in short, electrons are indistinguishable. Therefore, the electron probability density should remain unchanged when you exchange two electrons. Therefore, we have this equation. The probability density remains unchanged when you swap two electrons, when you swap electrons 1 and 2. And we can actually simplify this equation. Psi 1, 2 is equal to plus minus psi 2, 1. When psi 1, 2 is equal to psi 2, 1, we call those particles bosons. When psi 1, 2 is equal to negative psi 2, 1, we call those particles fermions. Electrons are fermions, and therefore the wave functions of electrons must be anti-symmetric. Anti-symmetric means when we swap two electrons, the sign of the wave function should change. And this is quantum mechanical postulate 6. Wave functions that describe a many electron system must change sign under the exchange of two electrons. And again, psi 1, 2 is equal to negative psi 2, 1. Now, when we construct a total wave function for a many electron system, we need to make sure the total wave function of all these electrons must be antisymmetric with respect to the exchange of all coordinates of one electron with those of another. And 2, we need to include the electron spin in the set of coordinates. So it's not just x, y, z of the electron, but also the spin coordinate of the electron. Now, how can we construct an anti-symmetric wave function? Well, we'll have to resort to the Slater determinants for a many electron system. For example, if you have two electrons, make a 2 by 2 determinant like this. All right? So you need to make two atomic orbitals, phi 1 and phi 2. And then you can put electron 1 in phi 1. You can put electron 2 in phi 1. You can put electron 1 in phi 2. You can put electron 2 in phi 2. Alright, so you have 4 elements. They're all different. And then how do we expand this? Well, very simple. It's a 2 by 2 determinant. So we can expand this as phi 1 of electron 1 times phi 2 of electron 2 minus phi 1 of electron 2 times phi 2 of electron 1. What about this? This is normalization factor. I'm assuming phi 1 and phi 2 are normalized. And to ensure this total wave function of both electrons is also normalized, you have to include this normalization factor. And remember, how do we normalize a function? We need to take the integral of the squared modulus of the wave function. So you need to kind of just, square this, and then you integrate it, square this, you integrate this, and the result is going to be 1. What if you have a 3 electron system? Well, this time you need to make a 3 by 3 determinant. You have 3 electrons, right? Electron 1, 2, 3, 1, 2, 3, 1, 2, 3. And then you need to have 3 wave functions, 1 for each electron. And these 3 wave functions, they have to be different. So let's name them phi 1, phi 2, phi 3. So phi 1, phi 2, phi 3 are 3 different wave functions, 1 for each electron. And then you can put electron 1 in phi 1. You can put electron 1 in phi 2 or phi 3. Same for electron 2. Same for electron 3. So you have a 3 by 3 determinant. You can expand this determinant and get 3 factorial terms. If you have a 4 electron system, you'll make a 4 by 4 determinant. You'll have 4 factorial terms. What about 10 electrons, such as water? You get 10 by 10 determinant. And then you have to look at 10 factorial terms. And that's a lot. Now let's look at this again. We have a normalization function. And then how do we expand this? Very simple. You have phi 1 of 1 times phi 2 of 2 times phi 3 of 3 plus phi 3 of 1 times phi 1 of 2 times phi 2 of 3 times phi 2 of 1 plus, times phi 3 of 2 times phi 1 of 3, and then minus, now you look at this this diagonal, minus phi 3 of 1 times phi 2 of 2 times phi 1 of 3 minus phi 2 of 1 times phi 1 of 2 times phi 3 of 3 minus phi 3 of 2 times phi 2 of 3 times phi 1 of 1. Well, if you're not familiar with the expansion of a determinant, you probably want to review the basics of linear algebra. Now, what are the properties of this determinant? Very simple. If you exchange two rows or two columns, the sign of the determinant will change. So that's really nice. So if you want to exchange two electrons, let's say exchange electrons 1 and 2, you simply need to exchange these two rows. And it's the intrinsic property of the determinant that if you exchange two rows, the sign will change. So let me translate this. If you exchange two electrons, the sign of the wave function will change. So this is to comply with quantum mechanical postulate 6. Here's a example, psi 1, 2, you can write this, and then because of the anti-symmetric property of the determinant when you swap two electrons, so I'm swapping 1 and 2, so you put 2 on top, 1 on the bottom, and then you need to have a negative sign here. And in this case, you are looking at psi 2, 1. So psi 1, 2 is equal to negative psi 2, 1. We just proved that this determinant is antisymmetric under exchange of two electrons. This wave function is antisymmetric and is in compliance with postulate 6. Now let me give you a more specific example. Let's say we have two electrons in the helium atom, both occupying the 1s orbital. Electron 1 is 1s in the 1s alpha orbital. Electron 1 is in the 1s beta orbital. Electron 2 is in the 1s alpha orbital. Electron 2 is in the 1s beta orbital. Alright, so it sounds a little strange. Why is electron 1 and electron 2 are both in the alpha and beta orbital? Remember this, electrons are indistinguishable. All you know is this, two electrons occupy the 1s orbital. 1 is alpha, 1 is beta. I don't know which is which. So you can use this wave function. Alright, and then we expand this wave function, and we have 1s1 alpha 1 times 1s2 times beta 2 minus 1s1 beta 1 times 1s2 alpha 2. And we see there's a common factor. The common factor is 1s1, 1s2. So the common factor is here. And then we have another term. This is the spin function. We have alpha 1 beta 2 minus beta 1 alpha 2. So now you can tell in this wave function there are three different components. This is the normalization factor. This is the least important part. This is just to ensure the integral of the squared modulus of the wave function is 1. That's it. And now let's look at this part. This is the so-called spatial function. Spatial function describes the position or the probability density of the position of the electrons regarding space. And right here, this is the so-called spin function. When you look at the spin function, if you change 1 to 2 and 2 to 1, you'll see the sign of the spin function will change. Again, let's look at this spin function. Let's exchange 1 and 2. When we exchange 1 and 2, you have alpha 2 beta 1 minus beta 2 alpha 1. And that's simply the opposite of this guy. So when you exchange the two electrons, the spin function changes sign. And when you exchange 1 and 2, well, this one is symmetrical under the exchange of the two electrons. Alright? So this is symmetrical, this is antisymmetrical, so the product is antisymmetrical. And we proved that this wave function is antisymmetrical with respect to the exchange of two electrons. The Polyexclusion Principle is a direct result of this antisymmetric principle. No two electrons can have the same set of quantum numbers. So in the helium atom, the two electrons have the same values of n, l, m sub l. So n is 1, l is 0, m sub l is 0, and they have the same s. S is positive 1/2. the value of S for any electron is positive 1/2. Okay, no exceptions. It's just always 1/2. The Z component of S can be plus 1/2 or negative 1/2, and that quantum number is M sub S. All right, M sub S can be plus minus S, and S is 1/2. All right. So if we allow this 2 electron to occupy the same orbital and have the same spin, we have a problem, a huge problem, because the two wave functions of these 2 electrons would then be identical. And I'm going to say, well, in this case, let's say phi 1 is equal to phi 2 is equal to phi. And then we write out this determinant, 2 by 2 determinant. Well, just by looking at this determinant, it's 0. It's phi of 1 times phi of 2 minus phi of 1 times phi of 2. That's just 0. The wave function is just 0. That means the squared modulus of the wave function is 0. That means the probability density is 0. That means the probability is 0. Also, we can use the property of the determinant to look at this wave function. So we can swap this row and this row. So we got this red column here and this one here. So after we swap 2 columns, look, there's no difference between these 2 determinants, all right, except this arbitrary coloring. And then this one, since we swapped these 2 columns, we need to add a negative sign here. And once we add a negative sign here, we say, well, this one is negative psi 1, 2. So now psi 1, 2 is equal to negative psi 1, 2. What does that mean? Psi is equal to negative psi. Have you ever seen this kind of equation? X is equal to negative x. Is that possible? Yes, when x is 0. So in this case, this equation holds only when psi is 0. But if psi is 0, then the squared modulus of psi is 0. That means the probability density is 0. That means the probability of finding these 2 electrons with exactly the same wave function is 0. There's no chance for you to find 2 electrons with the same quantum numbers. Oh well, if you have 2 different helium atoms, okay, that's a different story. Okay, that's a different story. You can have, 1s alpha, 1s beta in helium 1, and also you have 1s alpha, 1s beta in helium 2. Okay, so I'm talking about the electrons in the same atom. Okay, they cannot have the same set of quantum numbers. But if you are talking about 2 different helium atoms, well, that's just completely irrelevant. Okay, do not apply the Polyexclusion Principle to 2 different helium atoms or 2 different hydrogen atoms. If you have 2 hydrogen atoms, it's possible for the 2 electrons, one in each different hydrogen atom, to occupy the same 1s orbital and with the same alpha spin. Well, it's just because the 1s orbital in the first hydrogen atom is different from the 1s orbital of the second hydrogen atom. Well, they have different centers. Now, let's emphasize this. Any 2 electrons in the same atom, okay, in the same atom, they must either occupy different spatial orbitals or they have different spins. When they have different spatial orbitals, that means they have either different n or l or m sub l. When we say they have different spins, they have different values of m sub s. So that means, well, again, if you are looking at 2 electrons that occupy the same spatial orbital in the same atom, they have the same values of n, l, and m sub l. And then I can tell you these 2 electrons, one has alpha spin, the other has beta spin. I just don't know which is which. They just have different spins. Oh, but I just want to remind you, in many general chemistry textbooks, they don't mention this S. This S is the magnitude of the vector of electron spin in 3 dimensions. The value of this quantum number is always positive 1/2 for all electrons.